Hey guys, let's go ahead and do a couple examples using the integral test. So we did an intro which had some examples kind of built in, but they're not always going to just be the harmonic or just be 1 over n squared. So let's just add a little twist to it, and let's start. Let's see. Let's just pick one from the book here. How about this one? Okay. So this is not the excuse me. This is not the harmonic, so I can't just say, oh, it kind of has the 1 over n feel to it, but the 3n plus 1, we don't know if that's enough to alter it to make it actually converge. So we need to check it. And we can apply our integral test. It's a continuous, positive, and decreasing function. If I turn this into my integral, 3x plus 1, okay. And again, if for some reason you weren't able to tell that the function was decreasing just by looking at it, then you could actually determine that using our really old-fashioned techniques of taking the derivative, right? Increasing, decreasing. So if I take my derivative and I want decreasing, I want to make sure that my derivative is always less than 0. That would make it decreasing. That would make the function decreasing. So let's apply our integral test here. And I'm not going to draw any pictures anymore. Now it's just flat out grinding out the actual integral. So this is going to be the limit as t goes to infinity, 1 to t. And this, 1 to t. This integral is going to require a little bit of substitution. Okay, I can't actually do the antiderivative of 1 over 3x plus 1 in my head. Well, sorry, that's not true. I could, but I want to show this because I know some people have trouble doing it that way. They never remember, do I multiply, do I divide, what do I do? So if you let u equal 3x plus 1, du is 3 dx. So 1/3 du equals my dx. And that means I basically just need to pull out a 1/3. So I have the limit as t goes to infinity, 1/3, my integral of 1 over u du, right? 3x plus 1 turned into u, so that's here. My 1/3 du replaces my dx, so my dx is turned into a du with a 1/3. And instead of going from 1 to t, I'm going to go from 4 to 3t plus 1. Okay, and this is where some of you, your strategies differ from what I suggest. You like to resubstitute back in, which isn't the end of the world. You just make sure you remember to actually resubstitute. But I'm just going to do one full substitution all the way through, and then I never have to worry about it again. Okay? So this is the limit as t goes to infinity of 1/3, 1 over u. Okay, 1 over u is natural log of absolute value of u, but everything's positive, so I'm just going to write u, evaluated from 4 to 3t plus 1. Okay? So this becomes 1/3 ln of 3t plus 1 minus 1/3 ln of 4. Okay, the 1/3 ln of 4 is pretty insignificant here. I really got to focus on what's happening as t goes to infinity. As t goes to infinity, this goes to infinity. Ln of infinity is infinity. I don't care if I'm dividing by 3, that's not going to do enough. That's infinity. So this integral diverges. So therefore my series diverges by the integral test. And that's how it works. Okay? That's it. There's nothing else to actually do there. I think I'll do one more though. So this time I'll put one up and then I'll pause it and see if you guys can solve it first. And then it's basically going to be a homework problem, and then see if you do. So let me just grab one more. Let's try the series from 1 to infinity for e to the negative n. Okay, so let's compare that to our integral e to the negative x, and let's see what happens. Okay, so we've got, well, first of all, again, positive, decreasing, right? Continuous, so we're good to go. And let's go ahead and do our integral. Oh, actually, sorry, I wanted you to pause it first. Sorry, that's what I wanted. So pause the video, see if you can do this one. This one is one of your homework problems, and if you've already done your homework, then I don't really know why you're watching this video. But if you haven't done it yet, this is one of them. So why don't you pause it, give it a shot, and then come back to the video and see what happens. Okay, so pause it, and then come back. Alright, let's see how you did. So limit as t goes to infinity, 1 over t. Okay, and this one, I suppose I could do a U-substitution letting u equal negative x, but I think it's safe for this one to just know that there's a negative coming out of this, right? If I were to take the antiderivative, I would have e to the negative x over negative 1. So just to save a little time, I've got negative e to the negative x evaluated from 1 to t. Okay, so this is going to be the limit as t goes to infinity of negative e to the negative t plus e to the negative 1. Okay, so as t goes to infinity, I know at first glance you look at that, you're like, oh, e has, to a power with a t in it, I guess this must be going to infinity also. But this is to the negative t. So really, if I take one more step here, it might be more obvious. Negative 1 over e to the positive t plus 1 over e, if I do them both. And now I actually realize that the t is the exponent's in the denominator. So as t goes to infinity, that actually helps me, excuse me, because this is going to go off to 0, leaving me with just 1 over e. So in fact, this integral converges to 1 over e. Now, that doesn't mean the series converges to 1 over e. It just means the series converges, period, by the integral test. If I wanted to find the actual sum here, the only real way we could do it were the two techniques, or really 3 techniques we have. We could put it in the calculator and just do a billion terms or whatever and try to figure out what it's going to approach. It's still just an approximation. Or we can try telescoping, see if that works, that trick, that one little obscure little trick we did. Or maybe it's geometric, okay? And if it's geometric, we can find our series sum by using our geometric formula. And of course, coincidentally, this is a geometric series. In fact, you could probably see it already, but let me list out a couple of terms just for the fun of it, for the sake of review. This is going to be, 1 over e to the 1 plus 1 over e to the 2, 1 over e to the 3, 1 over e to the 4, etc. Sorry. And then, so to get from 1 over e to 1 over e squared, I'm multiplying by 1 over e. Multiply by 1 over e, I get this. Multiply by 1 over e, I get this. So my r is actually 1 over e, which is less than 1. Okay? And my a value is 1 over e. So my sum, my actual series sum, in this case I actually can figure it out, is going to be 1 over e over 1 minus 1 over e. And simplify that a little bit. It's going to be 1 over e. Let's see, this is e over e. So e minus 1 over e, right? Common denominator, put it together. My e's are going to cancel, and I actually get 1 over e minus 1. Now, I know it didn't ask for that, but it can't hurt to practice that because we should be able to do that anyway. Okay, so if you put that in your calculator, you could probably figure that out and see that it's going to approach. This is 1 over e minus 1. Sorry, a little messy there. I actually have a cat on my shoulder right now. Let me see if I can get that on the camera here so you can see it. See what I've been dealing with trying to make this video. Can you see her? See how I have to like hunch over while I'm doing this? Yeah, this is real comfortable. Yeah. Hey guys. Alright, anywho, there's a couple examples right from the book. So hopefully that helps with your homework. And in the next video I'll show you the P-series, which is sort of a shortcut for some of these, okay? Alright, let me know if you have any questions, and I will talk to you guys later.